In this lesson, we will study about diode and rectification process. What is rectification? Be that simply converting an AC signal towards a DC signal. Now, AC means that the voltage is always changing, and DC means that the voltage, even if it does change at some points or momentarily, it will still be causing the flow of current in one direction. So basically, it all comes down to the direction of current. That DC will cause the current to flow in one direction, and AC will change the direction of current at all times. Now, to understand the diode function, I'm going to give you a very, very brief introduction. If you want to go into the details, you can go and watch the video of O-levels diodes. The basics actually stem from them. So a diode is a device that causes the current to flow in one direction only. And the symbol of the diode is going to look like this. I'm not going to get into the details which one is cathode, which one is anode, because in this chapter, we're only interested where is the current going to flow. So the current flows in the direction of the arrow of the diode. This is an indication for the students to just make it simple for yourself. Don't get too complicated. Don't try to make this complicated in terms of naming the terminals that this is anode, this is cathode, so on and so forth. No need for that. Just know which direction of current will it allow to flow the current for, right? So if the current is actually in this direction, that means this terminal has to be connected with the positive terminal, and this terminal has to be connected with the negative terminal of the battery in this way. If this is the case, then the diode will most definitely allow the flow of current, because the battery is also causing the flow from positive to negative. And by this time, we understand that whatever current that we're dealing with in physics, that is the conventional current, which is from positive to negative. We don't have to deal with the negative current. We don't have to deal with the electron flow. It doesn't matter. Now, for example, if you had provided, let's say, and what are the different perspectives of positive and negative voltages? You see, voltage is dealt in terms of potential difference, right? So what does that mean? It means that in this case, the voltage at this terminal should be higher than the voltage of this terminal. If that is the case, then the diode will be considered as forward biased, which means that the current will be allowed. So for example, if this voltage is 8 volt and this voltage is 2 volts, the current is going to flow from higher potential towards low potential. So the diode will allow the flow of current, even though both voltages are positive. Now, for example, if one voltage is 10 volts and this is 0 volts, then again, this one is a higher voltage, this one is a low voltage. So from high voltage to low voltage, the current will flow through the diode. This will be forward biased. But for example, in a condition which the forward terminal has a high voltage and the backward has low, for example, 8 volts and this is 2 volts. This will be considered as a reversed biased condition in which the diode is experiencing a voltage that is causing or that is trying to flow the current in this direction from high voltage to low voltage. But since the diode arrow is opposite to the arrow of the expected current, remember I'm saying expected current, we're just drawing this arrow to check whether the current will flow. Otherwise, the current is not flowing. Please note, what students generally visualize when we talk about the reverse bias condition is that probably the current has started traveling. A very layman understanding that the current has started to flow, the current is flowing, the current is going over here, the current is going. It's not like car traffic example, that the cars actually come to this point and realize that, oh, sorry, there is a blockade and we can't go further. The current will not even begin to initiate. Why? Because they are all connected with electrons. So there are infinite electrons in this connecting wire. So that when this electron pushes the next one, the final push of the electron is felt by this electron. So when it realizes that there is a blockade, this whole path is actually blocked. Nothing can flow through the circuit, right? So reverse bias condition, the current will not even begin to start. But for the sake of understanding, we draw the arrows to see whether what is the battery trying to do. So the battery in this case is trying to cause the current in this direction. But since the arrow is opposite to the direction of the diode, the current will not flow. This is a simple understanding of the diode. Simple as that. No need to go further than this. So and if you want to go in depth, then you can try the O-levels video in which I have analyzed series parallel circuits of diodes and what are the common questions. So first we move towards half-wave rectifier. Now rectifier simply means that the current has to flow, or the current actually converts from AC to DC. But why do we call this half wave? Because only half of the wave of the AC signal gets to convert into a pulse of DC. We are unable to extract the full wave, although full wave is a part of your course, but let's see how it works. So we are going to use a transformer. Why we're using a transformer? So that we can change the level of voltages. Even if you provide this AC supply directly to the circuit, it wouldn't matter. But generally a transformer is involved to reduce the level of voltage from a high level to a low level. So you can ignore the fact of the transformer. Transformer is not the part of this lesson, at least. Now let's understand that this positive cycle of the current, let's label this as the red color, and the negative cycle gets labeled as the blue color, and let's say complete this one is the blue color. So the positive current, the positive side, is actually visualized in terms of sinusoidal, this being the positive side and the other one being the negative cycle. So what's going to happen in this case? So let's say if the current is in the positive direction, the current will try to flow like this out of the source in this direction. For the sake of assumption, let's say this is the current. So our expected direction of current matches the direction of diode. So this current will be allowed to flow through the resistor and then back to the secondary. When we go towards the negative cycle, we realize that the direction current has to be reversed from the initial assumption that we've made. So the initial assumption was that this positive current is actually in this direction, but now for the negative current, I will assume this to be in the opposite direction of the positive. So negative current actually starts from this direction, although positive started from this point. Now, when this now again, please be advised, negative current is not flowing. It will not come here and realize that, okay, there is a blockage. It will not flow to begin with. We just draw this loop to understand for ourselves that this arrow of the negative direction and the arrow of the diode are not exactly in the same direction. They are in the opposite direction, which means that this blue current or the negative direction current will be unable to flow. So what happens? Only the positive direction current is allowed to flow. Only the positive direction current is allowed to flow, but every time the negative current starts to initiate, it starts to come into the picture, it is not allowed to be. It is not allowed to pass through. It is not allowed to exist. So that is a graph that you see on the output, that this is the input, this is the AC signal that you provided, and this is the output. This is what you get. And please don't be confused by the transformer. What you could have done simply is that provide an AC supply, connect a single diode, and connect a resistor across it. This is the simplest understanding. So this is your V input that you're providing an AC signal. And if you connect a voltmeter across the resistor, that will be your V output. And that would be actually like this, pulsating, because positive current is allowed and negative current is not allowed. So positive current exists, positive current exists, positive exists. But the negative cycle, which was supposed to be like this, has been eliminated in this diagram, which is evident over here as well. So we are providing positive current. So the positive was allowed because the diode was forward biased, and the negative current, when tried to flow, the diode experienced a reverse bias condition, which was opposite to the direction. So the current was unable to flow. Since we are only able to extract half the wave as compared to the full wave, this is my full wave. I've only extracted half of it, like this one, and the rest of it that has been blocked by the diode. So that is why we call this as a half wave rectifier. And rectifier because it has to go from AC to DC. And your mobile phone chargers, your laptop chargers, your UPS even also employs this technique to convert VABDA's AC electricity to DC output, so that this can be used to store into the batteries, because battery is a DC source. Although not half-wave rectifier is used, we use the full-wave rectifier. So let's see how the full-wave bridge rectifier actually works. The idea is same. We want to make sure that the full wave can be converted into the output cycle. So even in this diagram, I'm going to consider positive to be my positive cycle, red color to be my positive cycle, and blue color to be my negative cycle. So we will start with the positive cycle, which is the red one, and see what happens. So the positive current is actually going to leave this terminal, then towards this side, towards this side, towards this side. Now when it reaches this terminal, it realizes it can go towards both sides. It can either go to the diode 3 or it can go towards diode 1. But we understand that diode 3 direction does not match with the direction of the current that is being expected. So since the directions are opposite, I will say that this is reverse biased and the current will not flow. You see, I'm just looking at the arrow's directions and predicting my movement. You don't have to think about forward bias, backward bias, reverse bias. Don't think about it. Just look at the arrows. So then the arrow moves like this. The current actually flows like this, and then it flows, and then it gets to this branch. Again, the current has two choices. It can go towards this side and it can go towards this side. Again, notice that this arrow direction is opposite to the direction of the diode. So the current will not choose this path, rather the current will choose this path. So it moves through the resistor like this, right? And then goes back over here through this branched wire, then here, and then it reaches to this point. It again has two choices, right? Now this is where that concept that I just taught you actually comes into play, that if the forward voltage is higher and the backward voltage is lower, the diode, even though both voltages are positive, the diode will be considered to be reverse biased. The current will not flow from a, let's say, high voltage 10 volts towards a low voltage. The current will not be allowed to flow. The back terminal, which is the reverse side of the diode, should be at a higher potential. This voltage should be higher than this voltage, only then the current will be allowed to flow. Now, when we reach at this point, this is not generally discussed in classes, that what's going to happen at this point? The current has two choices. It can go towards this side, diode matches the direction, and it can also go towards this side, the diode matches the direction. What will happen now? The diode will not go in this direction. Why? Because we know that voltage is work done by charge. We know that it is joules per coulomb. We know that it is actually the energy of electron, because work done and energy have the same unit. So joules means that we are actually dealing with work done, or we are actually dealing with the energy of electron, which is basically charge per unit, joules per coulomb. So when the electron, let's say we have a peak voltage of 12 volts. When the electron entered at this stage, it had 12 volts. It had 12 joules of energy for every packet of charge. But when it crossed through the resistor and then went back to the supply, its voltage will be a bit less. So this terminal of the diode receives an electron of 12 volts. So this terminal receives an electron of 12 volts. Rather, let's say that the resistor used up a voltage of 11 volts, or let's say 10 volts. Now the electron that is coming back over here only has 2 volts to offer, because 10 volts were taken by the resistor. So this terminal receives an electron that has 2 volts. Now we notice that the diode in this condition will be considered as reverse biased, even though both voltages are positive, because this one is higher, this one is lower. The current cannot flow from a high potential to low potential, or in the opposite direction of the diode. It cannot happen. So that is why the current will not choose this path. It will reject this path and go towards this path instead, which has a connection with the supply of 0 volts, because most definitely the current has to flow from a high potential to low potential, right? So this diode direction or path is rejected by this electron path, by this current, and it actually flows back to the supply like this. Now let's start with the negative, and this is the positive cycle on the output visualized in the graph. So this is my voltage of the resistor. So positive cycle has been successfully extracted from the supply voltage. Now let's see how the negative voltage is going to behave. So the negative current actually starts from this point, from this direction. It starts reverse to the direction of the positive current, which was red. It starts moving in this direction, comes to this point, and then it has 2 paths to go. It can go towards this side, it can go towards this side. And we know by this time it will reject this path because the arrows do not match. So it chooses this path, D4, to go through. And then when it reaches this point, it again has a choice. It can either go towards this side or it can go towards this side. Now we notice that the direction of the arrow and the direction of the diode are not similar. So the direction, this diode path will be rejected. D1 will be rejected by the blue current, and it will not flow through that direction. It will flow through this path, and then it will move through the resistor RL, then goes to this wire, goes to this wire, goes to this wire. And then when it reaches this point again, it reaches the same point as the positive current. When it reaches this point, it realizes that I have 2 paths to go through. It can go through this branch, it can go through this branch, but it will reject this branch. Why? Because the electron actually started its journey. The blue electron actually came to this point first. And when it actually was at this point, it was fresh. It has no loss of electricity, or energy, which is 12 volts. But when it goes through the resistor, let's say it loses 10 volts and then comes back with the remaining voltage at this terminal at 2 volts. Now, this terminal of the diode has 12 volts electron, and this terminal has a 2-volt electron. This will be a reverse bias condition. The diode will not allow the direction of current or the injection of current at this point, and this D2 path will be rejected, and instead the current will take the path of D3 at this point. Then goes back to the source like this, and like this. So since the path of the electron is complete, the path of charge is complete, we have successfully extracted the negative cycle of the graph as well. So this is full wave rectification. What we've done successfully is extracted both phases of the AC electricity as the output. Now right now they are pulsing, of course, they're pulsing between a positive maximum value and then 0, then positive, then 0. We notice this, but we acknowledge this idea that no matter if it is pulsating or no matter if it would have been constant from a battery source, the current always remains the same. It remains the same direction. It keeps the same direction if in the resistor it is always moving downwards in this situation. So since the direction of the current is remaining same, we will effectively call this as a DC supply. So what we have done over here, we have successfully converted an AC signal or AC supply to a DC signal. That is the circuit that is used in your UPS, that is used in your mobile phone charger, power bank charger, laptop charger. Why? Because we need to take the electricity from the source, from the electricity provider, which provides electricity in AC supply. So, but if we have to charge a battery with it, what are we going to do? We are going to first convert this into DC. So every charger, mobile phone, laptop, UPS, uninterruptible power supply, that is the UPS, has a rectifier, has a bridge rectifier installed in it so that it can take this from the source of FABDA and convert this into a DC pulsating signal so that this can be connected to a battery, which will be now charged because now this is a DC signal. Now, there is a problem over there. Now, there is a problem of this pulsating output over here, right? So how do we deal with this? What we're going to do is we are going to connect a capacitor on the output, which will be called a smoothing capacitor. Okay, so we are going to look at its effect later. But right now, let's see another implementation of the full bridge rectifier. This is an interesting implementation, although I've never seen this question in your past papers, but I'm going to discuss this nonetheless so that you can visualize that not only 4 diodes can do this job, but 2 diodes can also do this job. This is a transformer that has actually 3 terminals. It is actually made like this: terminal 1, terminal 2, and then terminal 3. So let me discuss the path of electron that is going to be taken with the charges. So first the positive cycle comes in, goes towards this side, goes to the resistor, goes back to the supply. Now then the negative cycle will come in, will start from this terminal, go towards this side, go to this side, reach here, then go through the resistor like this, and then back to the supply. Notice that red and blue currents are actually flowing in the same direction, right? So this is also a full bridge rectifier with using 2 diodes only. Again, the transformer is not important. What you could have done is used simply an AC supply, used a diode at this point, a resistor at this point, connect a third terminal over here, a diode like this one, and then connect it over here. Now, how do you design this third terminal is to actually rip off a wire in the winding of the transformer or supply by making a connection at this point, a connection at this point, and a connection at this point. Since this is not generally asked, I have not seen a question like this, I'm not going to go into the details, but I hope that you understand the 2 diode model as well for the full bridge rectifier. Okay, so let's see how to get rid of that rippling effect on the output. So we understand that the output of our signal has ripples in it like this. Now, this is not actually safe for the appliance. Why? Because we understand that at some point the voltage is 0 and at some point the voltage is maximum. So what does it look like to the appliance? What does the appliance actually feel? What type of current is actually flowing through the appliance? Is a pulsating current. What does this do? It is as effective, but it looks like that it is being switched on and then switched off, switched on, switched off, switched on, switched off. So the appliance has to go through multiple phases. Sometimes it's experiencing high voltage, sometimes low voltage, high voltage, low voltage. This will disrupt the function of the appliance and of course most definitely may lead to its malfunction. It may destroy capacitors, inductors, resistors inside the appliance. So this is not a good idea. So how do we tackle this problem? How do we deal with this problem? What we do is we install a capacitor in parallel to our appliance. This is a simple capacitor, nothing fancy, but we call this a smoothing capacitor just because of the fact that it is going to make this ripple a bit smoother. So what's actually going to happen? The capacitors, we know, store electrical energy, they store charge. So when you connect a capacitor, let's draw the graph when the capacitor is not connected. A pulsating output like this. Now, when you do connect a capacitor, what does it do? Actually, when the current falls below to a value of 0, when there is no current, when there is no voltage, then this capacitor, since when the current is actually going to flow through the resistor by the positive cycle or be that the negative cycle, some of the current is actually shared with the capacitor as well because it is connected in parallel to the resistor, and some of the current will flow through the resistor as well. So this current that actually flows in the capacitor branch is actually stored in the capacitor like a battery. So when at moments when the voltage becomes suddenly 0, what happens is that this capacitor that is attached in parallel to this resistor starts giving its energy that it has stored back to the resistor. So first, when the voltages were high, it took some energy to store it, and when the voltages were low, it will inject that energy back into the supply. And notice that this can't go back. If the current from the capacitor actually comes from this terminal, it can go towards this side, it can go towards this side, and in both directions the diode direction does not match the direction of the current offered by the capacitor. So there is no other way for the capacitor current to flow. Rather, it is only going to flow through the resistor. So connecting a capacitor in parallel does not disturb our rectification function. Rather, it actually provides the energy to the resistor when there is a sudden drop of voltage due to the rectification process. So what we do and how the graph is going to get modified. So this graph actually goes something like this. Peak attained, then the graph goes slow. Peak attained, graph goes slow. Peak attained, graph goes slow. So on the output, what we see is a graph that actually looks like this. Like this. Instead of those sudden ripples, the voltage falling down, we are now getting an output that is on average a bit more stable as compared to these abrupt changes that we were expecting. This is what we wanted to do, right? So now, how do we increase this smoothing effect? This is called, by the way, these are called ripples. These black lines, these abrupt changes are called ripples, rippled output. So by connecting a capacitor, we have converted this ripples into a smooth output or a much smoother output. Now, how to increase the effect of this smoothing? What you can do, a very simple and common answer is increase the capacitance or increase the size of the battery that you're using. If you don't understand what is capacitance, you can go back and check out the video of A2 capacitance so that you can understand how a capacitor functions. Anyway, so you can increase the capacitance or you can increase the resistance of the circuit. But usually increasing the resistance of the circuit is not one of the options because we can't change the circuit again and again. We can't change our circuit of the laptop. We can't change the circuit of our mobile phone. We can't change the circuit of, let's say, the UPS battery that we have. Since we can't do that again and again, the resistance factor in real life is not a viable option. So we have to go back to capacitance. Because this is plug and play, we just remove one capacitor and install a bigger one. Remove that one, install an even bigger one until you get the desired effect. So generally increasing capacitance is a good idea and improves the smoothness effect. Now, how does increasing resistance prevent this or increases the smoothing? You see, when the resistance of the circuit is high, then let's say these are the rippled outputs. Then if the resistance is high, then the current will be low. If the current is low, that means that the capacitor will not lose its energy quickly, because the current is restricted because the resistance of the circuit is high. So instead of falling off the capacitor abruptly, because capacitor is going to, in this time, in this region, the capacitor is offering its energy to the resistor. Instead, because the supply has gone to 0, so the capacitor supplies energy. That is why you see an output like this. So if you increase the resistance, what actually happens is that this fall of current is delayed. Previously, the current would fall like this. Because the resistance is low, current is high, energy will be taken from the capacitor very quickly. But if you increase the resistance, the current is restricted, the fall is somewhat slowed down. So as a result, the current slows down less, this voltage graph falls down less, and it has more time for this AC supply to come back up again to the maximum value and take charge from the capacitor back and then supply energy to the resistor. So increasing resistance and capacitance have an increased smoothing effect. And one more thing, in terms of capacitance, we have done time constant, which was pronounced as tau. Now, tau is equal to RC. What is time constant? Time constant was the time taken for any capacitor system, any battery system, to go from charging, during charging, from 0 to 63% of its original value. If it is discharging, to go from 100% to 36%, which is again a delta of 63%, exactly the same way as in the charging process. So this is actually time constant. So if you increase resistance or if you increase capacitance, this time constant increases, and since the time constant increases, it delays the charging process, it delays this discharging process even more. That is why the graph is going to get more smooth. Okay, all right, let's look at this question. Common question in terms of diode rectification. He tells us to find out the value of time t1. No issue, we have the frequency. We're going to use the formula f equals to 1 over t and replace t with f. We get t is equal to 1 over 50, which is going to be 20 milliseconds. This is going to come out as 0.02 if you are interested in grade 2 mathematics and you want to avoid prefixes. I would advise you again to remember and memorize prefixes and see how to use them on the calculator to make your life easy, at least in A levels. So t1 is up to this point. This means that my complete wave is completing in 20 milliseconds. So this time is in 10 milliseconds. So this will be at 30 milliseconds. A gap of 10 milliseconds is observed in one wave. So this is going to be 30 milliseconds. Then we have the peak voltage V0. You just have to read it from the graph. This comes out. You can stop the video at this point. Let me clear this out. You can stop the video at this point. Check for yourself whether you can count the boxes correctly or not. This is 17 according to my understanding. So this comes out as 17. He asks you the root mean square value. We've done this in AC electricity, that 17 will be divided by under root 2 and you will get your answer as 12 volts. The mean voltage, this is interesting in terms of ideas. You see, what is mean voltage? Mean is average. So when you take the average of a sine function, we have done this in A2 mathematics P3 integration, that when you take the integration of a sine function or of a cosine function, the answer is 0. So when you take this area and when you take this area, when you add them together, your answer will be 0. That's why the mean voltage is 0. Since the mean voltage is 0, it does not help us in the calculations. That is why we introduced the RMS concept. And to understand more about RMS concept, you can go back and check out the video of AC electricity to discuss and understand what is RMS. I've solved a question in that video as well. Let's come down to this common question. You will see this question again and again in your examination. He will ask you to draw the line so that it can perform the diode or at least full wave bridge rectification process. No need to worry. You will use a lead pencil, hit and try this option. I'm going to pause this video at this point. You can pause the video and see whether you can find out the solution to this or not. So let me give you the solution. Now the problem is, if you had started from this point, let's say by mistake, then you can see that if the positive current was coming in, it couldn't go there, it couldn't go there. It cannot go anywhere. So this solution or this direction of connection is not right. So if you're trying the hit and trial method, what if I connect this terminal, first terminal over here? Does my positive current have somewhere to go? Yes, it can go towards this diode, while this diode will reject its path. Okay, so now the current goes towards this side and the current cannot go towards this side because this diode will reject its path. So now I need to provide an alternate path to the diode. So I will connect my resistor over here. Okay, I will bypass the current. I will ask it not to go towards this diode, rather go towards this path. So the current continues my path like this one, like this. And now it's time to connect back the resistor. So I could have connected the resistor back to this point. So what will happen then? So this current actually comes to this point and it repeats that same idea, that when the current was actually at this point, it had higher voltage. At this point, it has passed through the resistor. The voltage is low at this terminal. So the current cannot flow from a higher potential towards a low potential. This current will not be allowed to flow through this diode. I'm just complicating this situation so that you can try all the options before you finalize how to draw this diagram. So then I connect this towards this terminal, and now the current has a path to go through. So now the current is going to flow through this diode, okay, and then I connect this terminal towards this side. So the current goes back to this side. Now, just to be on the safe side, let's try the negative current as well. So the negative current actually starts from this point. It goes toward this side, this side, this side. Then it goes to this side, through the branch, through the resistor. Now notice I've successfully ensured that the positive current and the negative current both flowed in the same direction. So my answer is 100% correct. But let's, for the sake of understanding, draw the complete path. So it goes through this branch, goes through here, goes through this diode, goes through here, over here, and then back to the supply. So both cycles, positive and negative, both of them are successfully flowing through this circuit. So I'm going to color those diodes that have been able to allow the current in the same direction during the rectification process. So over here, I'm coloring these diodes because this is the path for the positive current. This is the path experienced by the positive current, like this. Now, sometimes you will hear this word, or sometimes you will hear this understanding in books and generally classes as well, that during the rectification process, the parallel diodes actually conduct. Parallel diodes conduct. Where do you see this happening? You see, this one is pointing this way, this one is pointing this way, so we consider them to be parallel. This one is pointing this way, this one is pointing this way, we consider them to be parallel. So that is why you can see that two blues highlight up and two greens highlight up when positive and negative current are flowing through them respectively. I hope you understand what the rectification process is.